Welcome to John Nicol. He is an associate professor at the University of Rochester. And I met him recently and this is going to be so good. I said, you have to come do a tech up talk when after having lunch up in Rochester with him. And we're going to talk about quantum explain so that even I could describe it better than it's like a machine that multiplies things out faster. So with that, we're going to get started. I will ask you, as always, feel free to use the chat function. We use that if you have questions. I see somebody's already in there chatting. And you may ask a question that I'm going to get to, but if not, please ask. This is Quantum Explain, very basic. So, John, the first question is one I've gotten asked a lot the last few weeks since we started to promote this. And that is, will you speak English or physics? And I promise that the title says it all, Quantum Explained. So any thoughts?
Hi, Kathy. Thanks for that great question. First, let me start by saying thanks for the invitation. It's a real pleasure to be here, and I've been excited for this. So I love that question. I will, to answer it, do my best to speak English, but should I happen to slip into talking too much physics, please feel free to jump in and ask for clarification. One thing I did want to say, if you'll allow me just to expand on this for a little bit, is that as a physicist, my job is to figure out how the world works and to teach people how the world works. And I think we can probably all agree that the world we live in it's a really beautiful and interesting and sometimes strange place. The sky is blue. At night there are stars and planets and comets in the sky. And as physicists, we get to explain and explore how this works. But sometimes because the world is so interesting and so strange, we end up using kind of strange words to describe how it works. And I think it's really important for especially physicists to remember that we all share in this wonder about how the world works. And it's really important for physicists and scientists to be able to communicate that to everyone so that we can all appreciate and understand how the world works. So I'm really glad you asked that question. It's a really important topic.
To understand a little bit more rather than just turning the on button. So,
Right.
um, so let's go truly a basic question. What is quantum physics? I believe this sets the stage for our entire conversation.
Yes. So quantum physics is the theory we have that explains how the world works at the smallest length scales. So by small, I mean really small. I mean down to the level of a nanometer. So a nanometer is about a thousandth the size of your hair. So we're talking really, really small here. Yes, extremely tiny. And so at these really tiny length scales, the universe is very interesting and strange. So regular particles like atoms or electrons aren't just particles anymore. They're also waves at the same time. And waves, something like sound or light, isn't just a wave, but it's also a little bit of a particle at the same time. So because of this, because particles don't just behave like particles, but also like waves, there's some really strange things that can happen. So one of these is the idea of a superposition. So if I have an object in my left hand and one in my right hand, normally we just imagine, let's suppose I had just one. It can either be in my left hand or my right hand. There's nothing strange about that. But when we go to the nanometer scale, you can have objects that exist in what we call superposition states, where one object can have some possibility to be both in my left hand and my right hand, which is pretty strange,
Magic.
right?
Magic.
It's almost magic. And it actually gets even stranger than this. So I can have two objects at the nanoscale that are entangled. And so when you have two entangled objects, they're correlated in a way that completely defies our everyday intuition. And it's not something we ever see in the day-to-day world. So these two things, superposition and entanglement, are examples of some of the strange and interesting things that can happen in the quantum world at the nanoscale.
Now, moving on to the topic, let's talk about, we talked about quantum physics. Now we're into quantum computing and start to form a picture in our mind of what quantum computing is.
Sure. So let me bring up a slide here. So, well, before I do that, let me turn on my slideshow here.
Good. We love when scientists even have.
Oh, I know. I know. This is usually where I make a joke about needing a quantum computer to do this. Um, okay, so what is a quantum computer? How does it work? So the computers that you and I are using right now on our laptops or phones, they make use of transistors. So there are billions of transistors in the computers that we're using right now. And the transistor is like a switch for electricity. If the switch is on, electricity can flow. And if the switch is off, there's no flow of electricity. So we sometimes call these transistors bits, and we represent those two states on or off, maybe with a 0 and a 1. So in the computers we're using right now, we have billions of bits, and the bits are either 0 or 1, like this. A quantum computer is made of quantum bits. We call them qubits sometimes. This is the quantum version of the transistor. So the qubit can be 0 or 1, but it can actually be in this superposition state of 0 and 1. So it has a probability to be both 0 and 1 at the same time. If you like, it's both 0 and 1 at the same time. So the idea for why this is good for computing is that if you had the ability to prepare your computer in multiple states at once, there's an idea that this could allow sort of a parallel processing advantage. And there's certainly some truth to that. It gets even.
So the big difference, like I learned Fortran a long, long time ago. Everything was zeros and ones. That's what we did those cards, right? You probably are too young to remember the cards, but the difference is we could have punched a card that was a 0 and a 1.
That's right. That's right. That's exactly right. And in fact, it gets even stranger than that, because with the card, you can copy a card. You can make multiple copies of the card. And so in that way, you can make your program robust against any errors that occur. But one of the strange things in a quantum computer is that you can actually not copy the state of a qubit. So we have to be actually very careful about how we detect and correct errors. So it's a really strange and interesting form of computing. Um, when you have two qubits, so moving on from superposition, when you have two qubits, then you can have entanglement. And this is also very powerful. So if I have two regular transistors, two bits, they can either be both 0, they can be both 1. One can be 1 and the other can be 0, or vice versa. If I have two qubits, they can be in any of those configurations, but they can also be in this strange entangled configuration where they're correlated in ways that are very strange. And one of the things that this means is if I have two entangled qubits, if I manipulate one of them, it's as if I'm manipulating the other one at the same time. So there's also a sense in which there's sort of an economy or efficiency of operations here, which can be quite powerful for computing.
The,
Um,
can we just say qubit? It's a quantum bit, right?
quantum bit.
Okay.
It's a quantum bit.
It's the
Yes.
first time someone used qubit, I like had no idea what they were talking about.
Yes. Yes. I think there are probably two instances of the two acceptable uses of the term qubit these days. One is this, and then the other is I think the length of the ark that Moses built was 80 cubits or something like this. So that's a fun little nugget there. But I'm happy to say maybe a few things that quantum computers would be good for, and with these qubits that can be in superposition or entangled states, we know that quantum computers will excel at solving certain types of problems, and one of these is factoring large numbers. So every number can be decomposed into a product of prime numbers, and this turns out to be a really hard problem, finding those factors for large numbers. Really hard. If you were, for example, to give me a 10-digit number right here, it would take me much longer than I would care to admit to find the prime factors of that number. But the fact that that's a really hard problem is important because that underlies RSA encryption. So that's a common encryption method, and it's hard to decrypt because finding the prime factors of a number is in general a tough problem. But we know that quantum computers will excel at this, and so governments are quite interested in this. Another thing we know that quantum computers will excel at is calculating the exact behavior of molecules, for example. So it turns out that my favorite molecule, and maybe the favorite molecule of you or some of our listeners, is caffeine. It turns out that to exactly calculate what a caffeine molecule will do would take a number of transistors equal to the total number of silicon atoms on the planet Earth. We would need to have a computer basically as big as the planet Earth to calculate exactly what a caffeine molecule does. But a quantum computer could do this with just 50 qubits. So that's another example of the potential power of quantum computers.
So what are you finding in the caffeine?
We're finding what the electrons are doing in the various orbitals in the caffeine molecule. So it would be simulating the dynamics of the electrons in the caffeine molecule.
And it'll allow you to figure out what that does to our bodies.
Well, that's the hope, indeed. And if we have the ability to simulate something like caffeine, maybe we would have the ability to simulate a new kind of drug, for example. That's exactly the hope.
Got it. Cool. So you'd sent me a brief introduction for you, and just want to dissect that um, John is well, I cut out the part, but quantum mechanics of nanoscale objects, especially individual electrons and semiconductor quantum dots. So that's just one sentence. We talked about nanoscale, that's really tiny, right? Objects. Electrons, that's what makes power, right? Semiconductor quantum dots. Want to explain that one?
Sure. So perhaps you or our listeners have heard that term before, quantum dot. There are lots of different kinds of quantum dots, but at the end of the day, a quantum dot is something that we use to confine and trap basically individual electrons. So there are lots of different kinds of quantum dots. Maybe you have a quantum dot TV. In the quantum dot TV, for example, there are little either metal or semiconductor, really tiny spheres that act as small traps for individual electrons. So we use something similar. We use nanofabrication techniques and semiconductors to create basically a really teeny tiny box. And then in this box, we can put just one electron in it, and we can manipulate it, we can measure it, we can tell it to do whatever we want it to do. And that electron, it turns out, just that one electron turns out to make a pretty good qubit. So there are lots of different ways to make a qubit, but this is the one that we like to study in my group here at the University of Rochester.
Great. Let's see. So then goes on, Paul. Exploring new ways to transfer quantum information between distant spin qubits and heat and energy and nanoscale quantum devices. So let's talk about quantum information between distant spin qubits.
Yes, that's a great question. So I don't know about you, but I have never actually seen in my everyday life a particle in the superposition state or an entangled state. I have never actually seen something jumping from my left hand to my right hand without me doing it. I've never seen a situation where if I do something over here, it immediately affects something over here. And part of the reason that we never see that is things like the light and the sound and the heat from everyday life, they disrupt those interesting quantum properties. So when we're building something like a quantum computer or qubits, we need to shield these tiny things as much as we can from basically everything else. And the ideal situation in which to construct a qubit would be just to have completely dark, completely cold box where you put your qubit, and then we would hope that it would work well. But you can see the problem. Eventually, to make a quantum computer, we need to have lots of qubits, and we need to have the ability to control them and measure them. So we have to find a way to have the qubits interact with each other in such a way that they can carry out the calculation, but that also doesn't disrupt these delicate quantum properties that we like to make use of. So that's what transferring quantum information is about. We need to have these qubits interact with each other. And then the last piece, heat and energy. Whenever we manipulate these objects, we usually create some kind of unwanted heat or something like this. And so we're interested in ways to maybe get rid of that heat or possibly create little heat engines or refrigerators or something that we can use maybe to make use of that extra heat that we generated.
So the energy's gone out and you have a little collector.
Exactly. Exactly.
Interpreting the English for me
No, you're exactly right. You can have something that collects the heat and then does something else
with
useful.
it.
Exactly.
So let's get to what you actually do. And so, how does your work and that of the department? Also, I didn't say in the introduction that you're a director on the Center for Coherence and Quantum Science. Let's discuss how that work fits within the basics of quantum and
Great.
where's quantum computing going?
Great question. Great question. So let me back up just a little bit. So sometimes in the field, we call quantum 1.0 kind of the set of ideas of quantum physics that describes how the world works. And we call these days quantum 2.0 the idea that we can use these principles of quantum physics for useful technology. By the way, a great example of this is the semiconductor transistor. It turns out that one needs actually quantum mechanics to understand how semiconductors and transistors work. So the fact that we're having this conversation, believe it or not, relies a lot on the basics of quantum mechanics and quantum physics. So what we're doing at the university, and we're very happy and grateful, as you mentioned, that the university is supporting us through the Center for Coherence and Quantum Science, is we're identifying some of these major challenges that it will take to realize the full potential of quantum 2.0. And we're focusing on some challenges that we can address here at the University of Rochester in an academic environment to help push this field forward. So some of these problems include, for example, how do we understand why we need to shield these qubits from light and heat and sound? How exactly does that work? How can we do it better, for example? We're also looking at things like biomedical applications of quantum computing and quantum sensing and the like. And so there are a lot of folks here at the University of Rochester in many different departments, faculty and students that are actively working on this, working in this space. So it's a really exciting time for us.
And your career has been made on working on qubits.
My career has mostly been working on qubits, and one of the things that I really like about qubits is that there's both a technological aspect to it, but also a very basic fundamental science aspect to it as well. And so I really like that mix.
I didn't do this at the beginning. I'm a University of Rochester graduate, and I just want to point out that Meliora is in your background there. And that's what we sign off as, Meliora. which is ever better. So this is important to me because I used to use the little computer center, which now is back in the facilities as a little hut when we took the 1-0 cards down there. And now you have a beautiful new buildings or building, right?
Yes.
To work on all these things. So let's go to some of your pictures about your thoughts of the future timing of accessible quantum computers
Yeah.
and applications. Show us some of your pictures.
Yeah, let me do that here. So one of the questions that we often get asked in this field is, when will quantum computers exist? And the truth of the matter is they actually already exist. They actually exist now. So this is a very incomplete listing of some companies and pictures of their quantum computers. You've perhaps seen pictures like this of quantum computers on Netflix or online. This is actually something called a dilution refrigerator. It gets very, very cold. Remember how I said the ideal environment for a qubit is a completely dark, completely cold box. This dilution refrigerator is something that does that. So this is a picture of what Google's quantum computer looked like. IBM's quantum computer looks similar to this. There are different types of machines that look different, but they exist and they exist now. It's tempting to think of these as incredibly advanced, all-powerful machines. And while indeed they are very advanced machines and the achievement is remarkable, it's probably more correct to think of these as something like the first Wright Flyer airplane instead of maybe a supersonic jet plane. So, just like the Wright Flyer needed someone to lie down in the cockpit, you can see it if you squint here, and it didn't fly very high or very far, and you needed someone to kind of spot it. These machines are pretty primitive in what they can do compared to the full power of quantum computing. So there's still a lot of progress to be done, but again, these machines, they exist now, and many of these one can access on the cloud. So the early applications of these machines that we're already starting to see, that we're starting to see now, include sensing. So there are certain quantum instruments that can allow navigation in GPS-denied environments. Other near-term applications of these will include things like exploring and simulating molecules and calculating some hard logistics or scheduling problems. These applications they're slowly starting to come. It will be some time though before we have what we call a universal fault-tolerant quantum computer, something that can decrypt RSA encoded messages. And so just to go back to
RSA is
RSA is a type of encryption. It's a common type of encryption. This is the one that relies on the difficulty of integer factorization. The fact that that's a hard problem is what makes RSA encryption difficult to decrypt. So that we've sort of talked about the cybersecurity aspect of this, the drug development, financial modeling, electronic material discovery, and indeed actually cleaner fertilization are aspects that are similar to this idea of simulating molecules, so on and so forth. So, it's an exciting time to be in this field. At this very moment, the main market is probably still government and academic science researchers, but we will see more and more commercial applications of this technology in the future. And I can show you. Well, here's Schrodinger's cat here. I can show you one more picture here. This is a picture of, by comparison, a very simple quantum processor, but this is a picture of one of the things that we study in my group here at the University of Rochester. So there's a little semiconductor chip here, and right in here is a teeny tiny qubit or set of qubits that we use to conduct our experiments.
little qubits that we can't see.
That's right.
Um, we're getting some questions. Um, Malval Bahani Astrid, like that name. Will we one day have personal quantum computers like we have the traditional computer, or will it only be like enterprise licenses? And what type? This person said they've heard everything from 2032 to 2050 plus. So, if any magic to share with us?
So with the caveat that it's obviously hard to see in the future, it's certainly going to be the case that an enterprise license will be the first way in which people will access quantum computers. At least for the foreseeable future, it's unlikely that personal quantum computers would be feasible, and that's in part just because they're really bulky and they require lots of power, and they're quite expensive. Um, Already, one can access some of the different machines that I showed earlier on the cloud. As far as a timeline to enterprise applications, I would say that 2032 to 2050 is about as precise and probably correct an estimate as is possible to give right now. So 2032 is less than 10 years away, and we will certainly see increasing commercial applications in that time. Whether or not we will reach the real hard part is correcting for errors that occur in the quantum computer. So one can now make a quantum computer with many, many, many qubits, but they will be error prone, and the errors are particularly serious in quantum computers. And so finding ways to manage these errors is really the hard part. And whether or not we will have a universal fault tolerant quantum computer, even by 2050, I think is unclear to me. But I think it's a great question.
So, your magic hat of seeing the future. There are some practical ones, like how much energy do quantum computers use from Dorothy Edwards. And another one, Ashton is asking about wastewater from the power of the machines.
Yeah, this is a great question. They unfortunately use a lot of energy, and while there isn't water waste, some versions use cold water to keep an instrument cold, maybe much like a conventional supercomputer. This does touch on, I think, one of the important ethical questions, around modern computing as a whole, and let's say certainly quantum computing. And there actually is a subfield of quantum computing that's called quantum energetics, which is looking to answer this question: how much energy does it take, and how efficient can we make it? So I love that question. That's another great one.
And water waste, is there water waste?
So some platforms use cold water. I wouldn't say
I
that
think
it's
you
full
sort of,
wasted water, but um, certainly it creates a lot of heat that has to go somewhere.
so it's more heating. Um, Tiffany joined late. Um, so if you can weave in what a qubit is, but she wants to know how you got in, oh, I'm sorry, that wasn't Tiffany, different question. How you got into this field. What caused you to become a quantum physicist?
So how I got into this field was I started my research career in the field of magnetic resonance. So this is the branch of physics that explains how an MRI scanner at a hospital works. And believe it or not, that science, that physics is actually quite close to quantum computing. So sometimes when I talk about this, I say that all of our bodies have a vast number of qubits in them. And it's these qubits that the MRI scanner at the hospital manipulates and reads out to construct an image of our bodies. So I started in that, and then I joined another group that was working on qubits, and it was not such a big step for me because I had already worked in similar physics, and I really enjoyed the community and the wide variety of different work that's possible in this field. So those are the things that I enjoy, and what got me started in this.
That was from Rosemary. Um, she'll have to listen again to the seminar to get to the talk to get the qubit story. It was Tiffany was asking about new encryption algorithms that have been created through quantum computing, and she is expressing concern about the security aspect of being able to decrypt much quicker.
Indeed, yes, yes, this is a great question. So there are now post-quantum encryption algorithms. There are now encryption algorithms that are resistant to an attack by a quantum computer. And the government is in the process of setting up standards for this. So it's not so I'll say with the caveat that I'm not a cryptographer or a information security expert. It's probably not urgent that one adopts these post-quantum uh, cryptographic methods, but it's likely that within the next period of years there will be a move toward that, and then at that point the concern will be about decrypting messages that have been sent in the past and stored. But there is a path forward for post quantum cryptography.
So, another question from Malval Esther, who I don't understand. Can you talk about the intersection of LLMs and quantum computing?
Yes, yes. So quantum artificial intelligence and machine learning are fields that are coming along. Most most quantum artificial intelligence or machine learning right now probably focuses on using quantum computers to perform tasks that are required as part of a larger classical machine learning or artificial intelligence algorithm. So one could imagine a situation in which some of the math, for example, or optimization that's needed for a large language model could be done on a quantum computer, but the overall algorithm would still be the overall computational framework would still be largely classical. There are some other results that are looking at sort of a pure quantum artificial intelligence, but those are still in much earlier stages.
Lisa Colombo, how would quantum computing work for recommendation systems?
So uh, perhaps I'm misunderstanding or perhaps I'm not understanding the questions quite right, but there are lots of applications for quantum computing in, I'll just generally call it logistics and scheduling. So if you have like a finite number of resources and you want to spread them out in the most optimal way, there are many algorithms that quantum computers can run to solve those problems. And then the challenge becomes, how do you map the problem that you have and that you are concerned with onto the algorithms that the quantum computer can run? Typically, one of the hardest parts about working with quantum computers is actually coming up with algorithms that work on them and that are more efficient than classical computers. But we do have now a library of these algorithms that work. So if you have something that you're interested in, a first step is to ask, how does this problem I care about map onto an algorithm that we already know how to run on a quantum computer? Feel free to put more in the chat if I didn't get that quite right.
You were, thank you. So you must have answered it. But feel free. I'm reading one from someone I know, June. And I think it says, I don't know what STATUE, I just sent you a note, is. But anyways, I saw STATUE is developing quantum middleware. And when do you think this could be feasibly in the market? She's an investor. And do you think this would accelerate quantum to the market?
Yes, yes, this is another good question. So in quantum computing community, we often kind of call this, I think, the full stack approach to quantum computing.
Excuse me, she just clarified startup.
Startup.
She's reviewing a startup that's developing quantum middleware.
Yes.
Okay.
And so, in this community, we recognize that there's the hardware at the lowest level, and then at the highest level, there's the software that the user interacts with. But then in the middle, there are many, many layers that translate what the user wants to run into the most efficient um, schedule, let's say, that the hardware can run. And there are indeed a number of startups working in this space, and it is becoming actually it is becoming quite important. So I can think of a few examples where innovations not at the hardware level, but at a few levels up to help optimize how the hardware runs and optimize how what the user wants is scheduled onto the hardware have actually made a pretty big difference in the application space. So I think it's not too early to be thinking about these questions, and it will become increasingly important in the future.
But June, I will tell you that this is a long, long lead time.
Yes,
When you're at the very beginning of a funding, right? A startup, you expect 7 years. When we're talking about 35, 50, it might be a long lead time, but we can talk about that.
indeed.
Um, I just know June does startups. Um, oh, here's one from, whoops. Oh, okay. June says potential sooner for better calculating climate risk. So that might be a good startup. But Albert has a question. Would quantum computing help in Bitcoin mining?
That's
Any?
an interesting question. I don't know the answer to that. I do know that there are a number of applications in the finance space. For example, looking at portfolio optimization and, let's say, logistics and scheduling in general. I'm not sure about Bitcoin in particular, though. That's an interesting question.
Yeah, how it might intersect with that little niche. I was ready to almost say we're done, but let's see, we have time for one more. What basic knowledge is required to specialize in quantum computing, physics, computer? This is from Adeswa, and I won't try to say the last name.
This is a great question. So today, to get started in quantum computing, you actually do not need to know any physics. Um, some computer background and possibly some math background will help, but you do not need physics knowledge to interact with quantum computers or run algorithms on them. To be involved at the hardware level, that's where some of the more technical skills start to become valuable, and even physics skills start to become valuable. But to start working with these machines, to understand how they're useful for or not for businesses, and to be aware and ready for them, definitely does not require physics background.
So there could be careers in
Indeed.
this. Where would someone enter this if they weren't physics?
That's a great question. I would say it would depend a little bit on your career stage. There are, for example, MicroMasters and other related programs to help folks either upskill into quantum or perhaps transition careers. For the younger folks, a master's degree is a great place to start. Even a PhD in this can be a good place to start as well.
So we only have a couple minutes. Do you have anything that you wanted to share with us that I didn't give you the opportunity to share? Or these questions were great questions today.
Okay, I will take you off on this, and let me just show you a picture of, and I love this picture of Schrodinger's cat here. So this is a famous thought experiment. It's not real, it's a thought experiment. It's pretend in quantum mechanics. And in this thought experiment, there's a cat in a box, and the cat is in a superposition of dead and alive. It's not a real cat. And the purpose of this thought experiment is to just illustrate how something in principle that quantum mechanics allows but that we've never seen in our everyday life. So this is actually some artwork that was created by a University of Rochester student. And I just love this piece of art. It sort of nicely captures the weird science implications of this. It kind of grabs your attention and makes you wonder. So I think this is a really great piece of art, and it kind of captures the beauty and mystery and the intrigue of you, if you will, of quantum mechanics. And this is one of the things I really love about this type of science.
I think you did a really good job of quantum explained. I,
Thank you.
I can do much better at cocktail parties now
Perfect. Perfect.
in terms of my descriptions. But I want to thank you. I guess we picked the right month with Halloween, since
Yes.
this involved a little bit of mystery and um, thinking caps and the witch's hat, thinking of the future. And I especially want to thank you, John Nicol, from being part of the University of Rochester. And I went there because it was very science oriented and I love science. And that's the reason we have Tech Up, is because we love science. I want to thank everybody who joined us. This has been great, getting lots of hearts and thumbs up going across the screen. This will be on our website by tomorrow morning. You can use that QR code or just use www.techupforwomen.com, and you will find this under our talks. I also want to say that we're in the midst of going to be introducing a subscription series for more advanced tech up, and you'll hear more about that over the next month. But again, Meliora to John, this has been great. And thank you, everyone, for joining us to learn more about Tech Up and also about quantum.
Thanks very much, Kathy. It was my pleasure.
I don't think I'm going to come back in 2035 to see if you got that prediction right, but
Oh, I think you should.
you think I will?
I think you.
2035?
Oh, yes.
That seems like a long time from now. Okay, have a good one, everybody.